Good day, ladies and gentlemen. Welcome to today's lecture, a continuation of cardiac anatomy and physiology. And today, this time, we are looking at electrical activity of the heart. Remember, we have already discussed mechanical function of the heart, discussing the heart as a pump. And so now, we want to look at what are the responsible electrical physiological events that lead to the heart to contract. So we begin looking at electrical activity as a result of a number of histological and anatomical features that the cardiac muscle exhibit. So if you remember, the cardiac muscle is striated, so it is organized histologically into sarcomeres. It undergoes aerobic respiration. It is autorhythmic. It has autorhythmic activity, meaning even without external autonomic stimulation, they can actually undergo depolarization. They are connected through interconnected discs as cells, and so through gap junctions they are able to share electrical activity through sharing of electrolytes, leading to these activities being coupled, and they function as a syncytium. I've explained how the atria are separated from the ventricles by the atrioventricular link, so that the atria will contract at as one unit as a syncytium, and the ventricle will contract separately as one syncytium. Electrical activity. So quickly you will notice that there are two main types of cells that make up the heart tissue. So we have 99% of those are contractile cells that actually make up the artery and ventricular myocardium, while the 1% are autorhythmic cells whose sarcomeres and contracting fibers are very little, so they do not contribute to the contractile force of the heart. So let's look at the electrical differences that we notice between the contractile cell and the autorhythmic cell. So the contracting cell, for example, atrial cardiomyocytes and ventricular cardiomyocytes, undergo a situation where they are almost always at rest at 100 and minus 80 millivolts, and a sudden stimulation can send them into threshold potential, and they undergo depolarization, which is zero phase, and then they undergo early repolarization, and then they go into a plateau stage, then they go into, which extends the action potential, then they go into repolarization, and then rest again. So the zero phase is depolarization, which is a result of opening of voltage-gated sodium channels like a nerve. But the sharp repolarization is as a result of the potassium transient potassium channels that open fast and they'll close fast. Within the same period, calcium channels also open. As a result, there is influx of positive ions, at the same time balanced by the efflux of potassium ions. So this extends the action potential almost in an unchanged, what is called a plateau number 2. But these two close, and therefore the late potassium channels open and cause repolarization and sending the contractile cell into resting. This is different from autorhythmic cells, which do not undergo rest, such that the negative potentials always sends them into depolarization. So around minus 60 millivolts, they are supposed to be undergoing rest. But these potentials open what are called funny channels, F channels. They are called funny channels, but they are because they are opened by negative potentials, while the rest of the cells, negative potentials causes them to hyperpolarize and go into rest. But these ones, the autothermic cells, negative potentials or hyperpolarizing potentials open funny channels, which allow not only calcium flow, but also a sodium flow, such that these will send into the membrane potential, moving towards zero, becoming less negative. By the time it reaches a minus 40 millivolts, the autothermic cell is sent into depolarization, which is the phase 0. Now, phase 0 for autothermic cells is caused by influx of calcium ions. So the calcium ions is what causes the depolarization in autothermic cells. Then repolarization again is potassium channel opening, and this will send the cell into hyperpolarizing potentials. But as this repolarization reaches minus 60, again we begin to open uh, the the uh, funny channels, and there will be influx of sodium and calcium, and then again sending into depolarization just like that. So they don't rest. These are the ones that make up the autothermic cells or the conduction system. The SA node, the internodal pathways, the AV node, the Purkinjes, as well as the nodal pathways. So the autothermic cells make up what is called the conduction system of the heart. So we have the SA node connected to the AV node. The SA node, or the pacemaker cells, are found in the atria, and then we have the AV node, which is closer to the other uh, left atrium. Now, between the SA node and the AV node, we have internodal pathways that connect these two. They are also autorhythmic cells. The AV node is connected to the Purkinjes through what is called the AV bundle of His. It was described by His, so it is called the bundle of His. The bundle of His divides into right and left branches, which end up into the finer, smaller Purkinje cells, which are also autorhythmic cells. So when these cells, autorhythmic cells, fire their action potentials, they spread through the atria and cause the atria to contract. But because there is a time before the AV node is stimulated to allow the passage of these electrical impulses into the ventricle, the atria will have relaxed before the ventricles can actually begin to contract. Then we look at, we've talked about the conduction system. So in terms of contracting, the SA node contracts faster, generates electrical impulses, not contracting, generates or discharges electrical impulses at 70 to 80 beats per minute, the AV node 40 to 60, and Purkinje's 20 to 40. Because of this, it means that the SA node within a minute generates more impulses. Therefore, it shuts down the rest of the conduction system. Therefore, it is called the pacemaker. So when it becomes faster, the heart beats faster. When it becomes slower, the heart beats slow. So we will continue with the conduction system, and you will get more insights as we go.